We see here in front of us the graph for the sine function. And what we want to do in this video is to show that you can write all other trigonometric functions in terms of sine. You can even write all the inverse trigonometric functions in terms of inverse sine. In other words, sine is the only one you need. So let's get started with cosine of x. This is the curve that we want to somehow emulate with sine. So let's think about what relates sine and cosine. Sine and cosine are co-functions, and the co stands for complementary. So in other words, if we take cosine of x, the same thing as if we took the sine of the complement of x. In other words, sine of 90 degrees minus x, or pi over 2 minus x. And you see that that exactly emulates our curve. So let's save this little formula for our own use, because it will come in handy in the future. So the next function that we want to turn our attention to is cosecant of x. This one should be easy, and it has this graph here, because cosecant is defined as simply being 1 over the sine of x. You see that that is exactly the same curve. So that one was easy. Let's now do secant of x, which has this graph. So secant is defined as being 1 divided by cosine of x. And of course at this point we could just sub in with our formula from before. So 1 over sine of pi over 2 minus x, and we get the graph for secant. So we'll move on to tangent of x. Tangent of x is of course the same thing as sine of x divided by cosine of x. And again, just subbing in for cosine of x, we can reproduce the same graph. So the only remaining function is cotangent of x, which looks like this, and is defined to be cosine of x divided by sine of x. And again, if we just sub in for cosine of x, we see that cotangent of x is equal to sine of pi over 2 minus x divided by sine of x. So indeed, we can write all of the 6 trigonometric functions in terms of sine. Let's now write all of the inverse trigonometric functions, so the arc functions, in terms of arcsine. In other words, in terms of this here. So we'll start again with cotangent, or with cosine rather. Arc cosine of x looks like this. And again here we can think about the fact that cosine and sine are cofunctions, because it turns out that pi over 2 minus arc sine of x gives us the exact same curve. Now, what does that mean? That just means that we thought of it this way. Arc sine of x, what is that after all? Arc sine of x is an angle. It's the angle that you have to take the sine of to get x. So if I subtract that angle from 90 degrees, I get another angle, and that angle, since sine and cosine are cofunctions, is the angle I would have to take the cosine of to get x. And that angle is called arc cosine of x. So that's how those are related. Again, we can save this for our own purposes. Arc cosine of x is equal to that. And we can move on to, let's do arc cosecant of x, because again, cosecant and sine have an easy relationship. Cosecant is just 1 over sine, so if I take arc sine of 1 over x, I get the same curve, right? This was arc cosecant, and this here is arc sine of 1 over x. Same thing. So we can now move on to tangent and cotangent. Arc tangent of x looks like this. And it turns out that you can write that this way. Arc sine of x divided by the square root of x squared plus 1. You see that that graph is exactly the same as the one for arctangent. Now this might seem to come out of left field, So let's try to develop some intuition as to why that might be. If I had a right triangle with sides x and 1, then the hypotenuse would be square root of x squared plus 1, right? Again, this is a right triangle. And we'll take a look at this angle here, theta. So what we want to relate is arctangent and arcsine. So let's take tangent of this angle, and that would give us opposite over adjacent, right? X over 1, I'll just write x. And the sine of this angle. So the sine of theta would be opposite over hypotenuse, right? So x over the square root of x squared plus 1. And now if I just take the arcsine of this equation, of both sides, and arctangent of both sides of this equation, we'll have our answer. So the arcsine of x over the square root of x squared plus 1 is equal to, now if I take the arcsine of sine of theta, since those are inverse functions and our angle here is between 0 and 90 degrees, I just get theta. Okay, so now I'll take the arctangent of both sides of this equation, and again, for the arctangent of tangent of theta, I would here just get theta. And here I have the arctangent of x. So we see that these two thetas are equal to each other, so we can pull our equal sign across there, and we get just what we wanted, that the arcsine of x over the square root of x squared plus 1 is equal to arctangent of theta. So with that, we can return to our graphs and do the one function that we haven't done yet, arccotangent, which gives us this graph. So since those are also cofunctions, tangent, cotangent, we could write that this way, pi over 2 minus arctangent of x, which also gives us the same graph. And now we can just sub in the formula that we just derived for arctangent, which was arcsine of x divided by the square root of x squared plus 1. And again, we get the exact same curve. So we've written all of the trig functions and all of the inverse trig functions in terms of sine. So why do we even have the other ones? Well, it is nice sometimes to have names for things, right? You don't talk to your friends and say, hey, look at that animal over there with the tail sticking up in the air and the forepaws and the whiskers that stick out to the side and the ears that stick up in the air and that makes the sound brrr, right? You say, look at the cat. Be that as it may, if we wanted to, we could write all of the trig functions in terms of sine.